Hello everybody, we're going to be working on section N.4, which is linear modeling, or as many students would call this is create the equation. Usually in math, you're given the equation and then they use it to solve. For the sake of this unit, we're going to be working our way backwards to try to create an equation from a story or a table. So before we start that, though, I just want to make sure that we're comfortable with what I'm talking about, making a table, rates, starting values, and things like that. So if I was given this equation and I wanted to make a table, I could simply make an x and a y table here. And then I can pick whatever values I want for x. -2, -1, 0, 1, and 2 are almost always my favorite values to use for x, but you can use whatever you want. All you do from here is you plug in each of these values into this equation and then you solve. So for this top one, I get 3 times -2 plus 2, which gives me -6 plus 2, which is -4. Here I do 3 times -1 plus 2, which gives me -1. Here I get 3 times 0 plus 2, which is 2. 3 times 1 plus 2 is 5, and 6 plus 2 is 8. So I've made my table. I'm going to give us a little bit of room from my equation. This is the normal place we go. Now, what we've done before this unit is talk about rates, which means that as we look at the table, we notice that my y values are going up by 3. And we notice that our x values are only going up by 1, so we don't have to do any of that fancy converting the table. So that means that my rate of this problem is 3, but I also like to call this rate of change. Okay, the rate of change is 3. We also know that the 3 is going to be 3 times the x value. If we notice here, like 3 times 0, 1 times 3, 2 times 3, like we did in the equation. So what happens right here, this is going to be our rate, our component. 3 times the x value, if the rate is 3, so on and so forth. We've got to ask ourselves, where does that 2 come from? In this case, plus 2 means that for each of the values, you have to add 2 above 3x. So thinking about the equation y equals 3x, if I picked an x value here, like 1, 2, or 3, this would be 3, 6, and 9. But if we look at our table, 3x is 2 below what we needed here, so we needed to add 2 to our equation. So that plus 2 is how much above this equation you are, or you could also think of it as your starting value. So that plus 2 could also be where you started in the equation. So before we get too confusing here, I want to make sure that we take a nice step back and we talk about what we just figured out. With this equation right here at the top, you will always have an equation that you're going to have a rate and a starting value. The rate is what we used to find out in the table. That's from section N.3. But when we move on to the next section, which is the starting value, which is right here, that's how much above the regular equation you are, or where your x equals 0 point is. Either one of those would be good. Now let's look at what it actually means in an equation. So if I have an equation here, this equation goes up by 1. So that means that our rate, or our average rate of change, is 1. So we look at our core equation as y equals 1x. But we got to figure out how much above that we are. So y equals 1x would be 1, 2, 3, and 4 for our y values, but we have 17, 18, 19, and 20. which means that we are 16 above in every situation. So y equals 1x plus 16 would be this equation. The way you check this answer is pretty simple. You just make a new table over here, and you just pick some values, and you see if they match. 1 times 0 plus 16 is 16. 1 times 1 plus 16 is 17. 2 times 1 is 2 plus 16 is 18. And 19, which does match up with our table here on the left. Now, I also talked about that x equals 0 point. If you notice the pattern is going up by ones, that would make this have to be 16, which also fits into our starting value point. Okay, so you find that rate of change, and then you have to find your starting value. I want you to try this one on your own. So for this one, it's a little bit trickier. These still go up by ones. So our rate here goes up by tens. We don't have to do any fancy stuff with it. So that means that our equation here is y equals 10x. But we got to figure out how much above our standard equation we are, or where did we start? Well, in this case, we're actually given the x equals 0, or the starting value. So 10 times 0 is 0, has to be plus 46 here for our equation. All right, so y equals 10x plus 46. I really highly recommend to just restart your table over and see if it works. 10 times 0 is 0, plus 46. 1 times 10 is 10, plus 46 is 56. 2 times 10 is 20, plus 46 is 66. 3 times 10 is 30, plus 46 is 76. All right. Now, the question with these always is, why are we doing this? Where do we learn this? What do we actually use it for? So we're going to move on to a problem where Trey and Mr. Schmidt are having a basket shooting contest. Mr. Schmidt makes 5 baskets every minute, while Trey makes 7 baskets every minute. Trey's obviously better here. However, Mr. Schmidt is given a 10-basket head start. How many minutes would it take him to catch Trey? It's a little Freudian slip there. So, before this section, we could have solved this with a table, and I'm still saying that the table method would work here. But since we're working on where do we use linear models, this would be a good time to take a look at how we could solve it by making equations. Well, Trey's is pretty easy, actually. He's just going to be y equals 7x. Pretty straightforward, nothing too complicated there. But Mr. Schmidt, on the other hand, he's going to be y equals 5x, but he's given a 10-basket head start, which would make this plus 10. And if we make a table here of minutes to baskets, minutes to baskets, we can think of minutes as our independent axis and our baskets as our dependent axis on both of these. So Trey's is pretty easy. I'm actually going to extend the page here. It's going to be 0, 7, 14, 21, 28, 35, 42, and 49. Mr. Schmidt's, by extension, is going to be a little bit tougher. So this is going to be, he has the 10-basket head start. This will be 15, 20, 25, 30, 35, 40, and 45. So if we look at our table, we got to find out where they match up, which appears to be 5 minutes, which means it'd take 5 minutes for Trey to catch up, and then Trey would beat Mr. Schmidt from 6 minutes on. So that's where we would use this linear modeling. Now you're going to have a couple assignments here on iExcel, and then a couple assignments on Google Drive, and then you will have an activity at the end of the unit called the toothpick activity. If you have any questions, as always, please let me know as quickly as possible.